Welcome to our very first discussion regarding our lessons in differential calculus. So in this video, I will be discussing all about functions. So this is our first topic, or one of the major topics that we have to discuss first, but this is just an introduction of all the things that you will learn in this lesson. But the very thing about this is that this is the root of all the things that we will encounter in your classes. So let's get into it. So what you can see now in your screen is a simple definition of relation and the function and some table. So what is into it? Let's just first describe what are functions, and before anything else, before we could describe it and use it in some more complex operations, we need to define what a relation is first. So a relation, so kung tatagalogin natin, it's a relasyon. No? A relation, by definition, is a set of ordered pairs x, y on S with x and y being an element of a set S. So it simply means that when something, for example, you have an x here, as you can see, meron tayong x dito, and then if you wanted to have an ordered pair, so if you want to, for example, give yung katambal niya, kasi nga may isang relasyon, so let's try to probably make a pair with them with -1, and then let's say 2 we have 7, and then for 3 we have 4, and then 4 to 6, and then 5 to 8. So what we have here are set of ordered pairs such that for every x there is a certain value for y, and when we write it in an ordered pair, we could simply write it as something like this. So -1 and then 2. So that is I'm gonna change the thickness. So let's say the ordered pair is -1, 2. So with that, you could say that 2 -1 is really different from -1, 2. And in that case, we call this the ordered pair. Dahil nga, iba kasi siya pag binaliktad natin. And simply, yung ordered pair natin is something na meron tayong sineset na x and then y. So parang ganun lang siya, x, y. So that's how we can simply define what a relation is in a simpler term, no? So if I would be writing all the ordered pairs that we have here 2, 7, and then we also have 3, 4, and then we have 4, 6, we also have 5, 8. So these are all relations. I mean, if we are able to give an equivalent expression for this, then we would call this all of them as relations. And technically, if we would just simply look at each pair, basta meron siyang yung x, meron siyang relationship dun sa other number na yun, then we call that a relation. And if we talk about function, it is a special kind of relation. Bakit? Kasi kagaya nga nung sinasabi lagi natin sa function, it is a special kind of relation. Parang sa relationship din ng tao, nagfa-function lang siya once there is a good relation. So parang siyang ganun, no? So what we do here is simply check on these values. Sinasabi natin na a function f from a set D into a set R is a rule that assigns each value of x as an element of D and each y as an element of R. So we call this all the values of x here the D, and D stands for the domain. So all the values of x that we have here are called the domain. And then these values of y here, we call this the range, or simply the R. So these are the domain and these are the range. So if we wanted to find a function from all these values, then what we will get here is simply a function when yung pair nung, yung value ng x is explicitly given into a certain value of y na distinct. What I mean is, kapag meron kayong value ng -1 here, isa lang yung kanya dito. So, in short, kapag meron kayong relation at kung strictly 1-to-1 lang yung relation nyo, then you're a function. Nagpa-function kayo. Parang ganon. Kasi diba, pagka meron tayong relationship, magpa-function lang itong relationship kapag meron lang tayong 1-to-1. Ang isang tao para sa isang tao. Kapag naman nagkaroon na ng yung hindi ito 1-to-1, so may problema pag ganon So, what do I mean by that? For example, yung -1 to natin is strictly, yung -1 is for -2 lang, But, what if yung -1 din, nagkaroon tayo ng papunta sa 6? So, with that, yung -1, 2, and then -1, 6, hindi na siya function kasi nga, nagkaroon na siya ng ibang ordered pair dun sa set of range natin na nandito, And, if you will ask me kung siya ba ay relation, yes, it is also a relation, but it is not a function. So, what we say about functions that it should be 1-to-1. Okay? So now, let's try manipulating itong ating arrow na to, So, let us try removing all these arrows and start something na iba naman para try natin or makita natin kung ano ba yung sinasabi natin na other kind of relationship using this arrow. So, never mind these ordered pairs now. So, for example, I have 2 and then 2 and then we also have 5 going to 2 and then let's just have some 3 to 6, 1 to 4 and then let's say 4 to 8. Okay, so meron tayong na left out na isa from our range which is 7. So, if I would ask you, is this a function or not? So, if you say no, kasi nga po, nagdalawa na siya, sabi niya po 1:1. So, that is incorrect. Though function should always be 1-to-1, it could also be many to 1. The previous arrowheads show that we have a 1-to-1 function. Then this one, remember, 5 and 2, we considered, sabi nga natin sa English, more than 1 is many. So, many, and then the value goes to y, which is just a one value, which is 2 in this case. So, yung 2, 2, and then 5, 2 is a many to 1 relation, parang ganun. But it is also considered a function. So, ang general rule natin is, kailangan magamit natin itong mga nasa dominant to once lang. And then, even though we have, for example, the same values for y, it is still a function considering na we're just only using these values just once. Parang ganun lang, I hope clear na kayo dun sa ating description ng function and relation. Basta ito naman is a review of your high school days nyo, or senior high school na for every function, there should always just be a 1-to-1 or many-to-1 relationship. Okay? And else, ito ay tatawagan natin relations. Now, with that, let's just try to answer this question. True or false? So, number 1, a function is always a relation. So, is it true or false? So, if you answered true, then you are correct. So, this is true. A function is always a relation. Now, number 2, a relation is always a function. If your answer is false, then you're correct. So, a relation is not always a function. Because if pag ginawa natin siya ng, let's say, parang siyang parang, let's say, this is the set and this is called the relation. So, yung function is like just a subset of that relation. So, parang ganun siya, That's why, hindi siya pwedeng magkabaliktad. Okay? So much for that for functions, relations, and function. So, we also have the domain and range. So, na-explain ko siya kanina na the set of all x values, given na siya yung independent natin, are called the domain, and all the values in y with respect to the values obtained from a certain function by substituting x from that function is called the range of the function. Okay, so magbigay tayo ng isang function. Let's say we have f of x equals x squared plus 7x, okay, plus 1. If given tayo ng independent variable na x, so any value of x is pwede dito kasi makikita natin na wala siyang restriction. Pero I will be explaining it later on, yung mga kung paano naghahanap ng restriction or what kind of functions are those. In this case, it is an element of all the real numbers. So, kapag sinubstitute natin yung mga values na mapoproduce natin from the values of x, then what we get is the range of the function f of x. So, let's move on with the type of functions. Now, there are just two major types of functions when we study calculus, and these are the algebraic functions and transcendental functions. Now, the ones written in a dark blue color are algebraic functions, and the one that you would see on the latter part would be on dark green. So there are transcendental functions. Now let us start with what is algebraic function. So an algebraic function is a function in which the operation is simply algebraic, meaning we obtain all these functions by simply adding, subtracting, dividing, and multiplying. Those are just the simple operations that we have in algebraic functions. Now in transcendental functions, what we do is that even though there are a lot of multiplication, division, you cannot obtain the values by just simple operations like that. That's why it is called transcendental, because it transcends algebra. Okay, so you later on you will understand what transcends algebra, and it's really easier to remember transcendental functions because technically it looks more different than algebraic functions. Okay, so with that, let us first discuss the algebraic functions. And the very first one, or the easiest to remember, is the constant function given by f of x equals c. C is the constant, and it will always produce a horizontal graph. So, if that's the case, then if I wanted to have some constant function here, so this is a constant function. It satisfies all these conditions. It is a horizontal graph, and when we talk about C, for example, this is a let's just do some number lines. So this is actually 0, 1, 2, 3. So it is at 0, 3. Therefore, the equation can be written as f of x equals 3. So with that, and f of x can also be written as simply y. So y equals f of x, which is equal to 3. So that is a constant function. So a constant function can also be written, or not written, but can be expressed as a line. Okay, so that is a line. And if you would, let's say, give the equation for this function, you would say it's just the same, sir. It's f of x equals negative 3. You are correct in a way that the equation is correct, but we have to remember that this portion here is a closed interval, and it just has the domain of 1, 2, 3, 4, 5, from negative 5 to 1, 2, 3, 4, 5, 6, 7, 8. Of course, this is just an approximation of the number line, so x would be just from negative 5 to 8. So, close interval. So, with that, what we mean by this is that the domain is just the elements of all the real number from negative 5 to 8. So, yun, hanggang dun lang siya and di na siya pwede lumampas doon. So, that's the difference between having a line and this is actually a segment if you want to describe it in geometry. Okay? So, there are some functions that look like this. So, the idea is that if it is given by this kind of function, then it is a constant function. Okay, now we proceed with the next one, which is linear function. And I believe that linear functions are more common than, these constant functions, simply because we usually solve for linear functions rather than constant functions. So with that, let's try drawing a simple graph here. So with that, we have drawn a linear function. And f of x equals mx plus b is a very familiar equation. So when you say linear, the degree is simply 1. The degree of x here is just 1. And the most prominent, characteristic of a linear function is its slope. The slope of a function is simply the change in y over the change in x. So if I would take something, let's say I have here, so let's make this one x sub 2 and then this one is y sub 2 and then x sub 1 and then y sub 1. But for as long as you don't get confused with the representation, it doesn't matter actually. So with that, let's try to evaluate what is slope. So we say that slope, or m, is simply the change in y over the change in x. So in simpler terms, we call this the rise over the run, and that is simply delta y over delta x. And with that, if this is delta y, then this is simply the change, and we call this y sub 2 minus y sub 1. And delta x is simply the change in x, which is x sub 2 minus x sub 1. And sometimes they still refer to this as the change in y over the change in x, which is a very familiar term that we use in calculus, which is usually we represent this as y prime, or the derivative of x. And that is how we were able to derive the definition of a function, the definition of differential calculus through the use of a slope, which is the rate of change. Okay? And by the way, we have to specify this m and b. The slope and the intercept should be elements of real number, of course. It shouldn't be complex. Okay? So yeah, this is a linear function. So linear functions can have a negative and positive slope. With this one, since it is increasing from left to right, then this is a function that has a positive slope. This is a function that has a positive slope. Now, if I draw another line that goes like this, so in this case, this line is directed from left to right, going down. So this has a negative slope. Okay. And let me just remind you that if the slope is 0, we will obtain a constant function. And then if the slope is undefined, then we will get a vertical line. Okay? And of course, that's not a linear function anymore. So let's proceed with the third, which is the quadratic function. So a quadratic function has an equation of f of x equals ax squared plus bx plus c. A quadratic function looks like this. So this is a very familiar figure for you, no? And this is actually what we call the parabola. So a quadratic function, given we have an independent variable, we will have a parabola here that looks like this. And the parabola would have some parts like the directrix, the focus, and the vertex. So these are the common parts of the parabola. And it is usually given by y equals ax squared plus bx plus c. So a, b, and c should be elements of real numbers. Okay? So much for that for the quadratic functions. And by the way, if if you remember your parabolas, we also have something like this. So this is not actually a function because, or not, this is not a quadratic function, because if you would write something like a parabola, this would have y squared rather than x squared. Okay, so with that, this is not the quadratic function that we are referring. This one, and then we also have this one. Okay, so these are the quadratic functions that we are referring. Now let's proceed with the polynomial functions. So a polynomial function is something that is that has a degree that is above the quadratic function. So it means that, for example, I have let's say a lot of variables that have a lot of degrees. Let's say 2, 3, 4. Actually, quadratic function is a polynomial function of degree 2. But let's just focus more on giving polynomials with degrees greater than 2. So let's try to have something like this. So this is, let me draw it again. So this is a kind of polynomial function. What is evident to polynomial functions are the critical points and then the maximum minima, which is determined usually by the degree of the highest degree of our independent variable. So it is always necessary to check on the sign of our exponent, because if we have a function, let's say f of x, let's just give an example. If f of x is equal to x cubed plus x squared minus 3, so this is a polynomial function of degree 3. But if we have f of x equals x cubed plus x to the negative 2 minus x plus 1, so we've got no problem with this x cubed and the negative x and then 1. But we do have some problem with negative 2, because it states here that n is a non-negative integer greater than or equal to 0. So this can be 0 but not negative. So this is already not a polynomial function. And sometimes these are very confusing items, and I hope you don't get confused with it. And most of the time, these kind of functions do not exhibit being called a function. They just become relations either way. So with that, if it's already clear, then let's proceed with rational functions. And by the way, these are just a review of your classes when you were in senior high school, so I'm just having it in a very fast manner. So, rational expressions are polynomials of degree n and m respectively. So, a polynomial function is usually a function that has an asymptote. Okay, so usually it is given by f of x equals p of x. So depending on the degree of the polynomial, but generally this is the representation of our polynomial function. Let's say we have x plus 4 over x minus 3, so something like that. So if, for example, we have this equation, then this will have an asymptote at 3. So I'll be discussing about this when we have arrived in the extreme of values and graphing. But for now, let me just give something like this. So the horizontal asymptote here is 3, and then if we wanted to set it to 0, then we will get something like horizontal asymptote. So you could just check on the graph, and then we can graph this, and we will obtain rational functions. And of course, you should be using some table, because such kind of functions, they are not easily graphed like those that we have given before. So let me just use a table function for now, and I'll just be graphing it from let's say negative 3 to positive 5. Okay, so So based on the table, so you don't have to like do something like this. No, I just wanted to show you how this how the graph looks like. So if I would be graphing this, I will get something like something like this. Okay, so it goes something like this, and of course I should be careful not touching this asymptote. No? And then if I have 1, I will get sorry, if I have something like 4, I will get some 8 here. So I think the graph would look like this. Okay, so this is the graph of that x plus 4 and then x minus 3. So in the latter part of this subject, you will learn how to graph such kind of functions, but I would assume that you already know how to graph this. It's just that we do have something like an asymptote, which is what we call the saddest story in mathematics. Na you can come very close, but you will never get to know each other, sabi nga nila, no? So rational functions are algebraic functions still, because the separating fraction line here is technically division. Okay, so with that, let's move on with the power functions. Power functions are, they're just the graphs that goes from 0 to hero. Because, for example, I have 0 here, then that will be 0 raised to r. So any number raised to 0 would just be 0. So it start with 0, and then if I have, let's say, x is 1, and then r, let's say r is 3. For example, let's try graphing this. Let's say 4, and then x, let's say, cube. So if I have 0, then I will get 0. If it is 1, then I will get 4. So 1, 2, 3, 4. So this is the point, and then let's say 2. So we get 8 here, and then times 4, so that's 32. So the graph is actually it exceeds this, this white paper here, but it grows really, really, high. And if it is negative, then it goes from 0 to down here. But what is evident in power functions that they are just like a single term from the polynomial function that we took out, and then we just wanted to represent it in terms of their individual property in a Cartesian coordinate plane. So that's how the power functions work. Okay, so yes, and then we move on with the first and the most common of the transcendental functions. So remember, transcendental functions are those functions that transcend algebraic functions, meaning they are not we can't solve them, we can't obtain them by just simply using algebraic operations. So in the first place, we get trigonometric functions, and we're referring to these 6 circular functions, namely the sine x, cosine x, tangent x, cosecant x, secant x, and then cotangent x. So the ones that are opposite these main 3 functions that we have are the reciprocal functions. So when we divide sine x, 1 divided by sine x, we get cosecant, 1 divided by cosine x, we get secant, and then 1 divided by tangent x is cotangent x. So let's just have something like a graph of sine x. So when we have sine 0 degree, so what we get is 0. And then when, let's say, we have here, let's say pi, so what we get with pi is simply sine pi is actually sine 90 degrees, which is equal to 1. So let's have here as 1. And then when it is, let's say, I'm sorry, it should be pi over 2. And then this one is pi. So when we have pi over 2, sine pi over 2, or sine 90 is positive 1. And then we get pi, we have here 0. And then when we have here 3 pi over 2, so we get negative 1. So in this case, what we get here is this kind of equation, this kind of graph, and it is a wave graph. So that's how our trigonometric functions look like. So I will not be dealing much more about this because we'll be having a separate discussion regarding this transcendental functions when we move on to our next topics. Now we also have the logarithmic functions. So this is a very this one is one of the basic or the most common thing that we learn in high school about the logarithmic functions. And the general expression, as you can see there, is f of x equals log of x base a. And a is an element of a real number, so that must always be the case. Okay, so now let's try solving for one function of logarithm. So let's try f of x equals log of x base 4. So with that, remember, this is a transcendental function, so it is quite difficult to, find all the values of y by just giving the values of x's. So I will be needing a calculator to find some points here in the graph. So let's try having 0. So when we try solving for x being equal to 0, what we get is an error because remember, this is a logarithmic function and you can't just simply have the logarithm but that will result to, because this log of x base 4 can be written as 4 raised to a certain f of x is equal to x. So if we wanted to, do something like 4 f of x which is equal to 0, can you think of a number that would result but that would give 4 raised to that number equal to 0? So it is impossible, so we don't have any value for 0 here. That's why x equals 0, or simply the y-axis, becomes an asymptote for all the logarithmic functions that we have. Now if this is the case, then if x is equal to 1, then that's the case when f of x is always equal to 0. So in all logarithmic functions that looks like this, so you will always get a function that is the unordered pair that is equal to 1, 0. So you always have this point. Then if you proceed further, we get some the graph would increase little by little, and that's how our logarithm works. So at 4 we get 1. So remember, this increases, and then is it possible that you would get let's say a value that is lower than these 1, 0? So if you wanted to try, let's say x is negative 0.5, of course you will get that value which is negative 1/2. So that doesn't look so good. So yeah, that looks better. Remember, this graph won't be crossing this region here, the negative region. It's just that it will just go down here, but it will be asymptotic to our y-axis. So this is the graph of a logarithmic function. So with that, I hope you understood this kind of function. The discussion is quite fast because this is just a review of what you've learned in your senior high school. Next is about the exponential functions, and if we have something like a logarithmic, we need to have an exponential functions. They're like I need to change something here. So this one should be an exponential function. Let's say a raised to x. Okay. So I'm sorry for not editing that before we record. I didn't see it. Okay, so with that, um, so let's have an example of an exponential function. So let's say we have f of x is equal to, let's take the one of the most common, with the Euler constant being e, and then let's say we have here 2x. So this is an exponential function, and this is a kind of transcendental function, which is in which you could just use the logarithmic function to redefine this equation. So with that, if we want to evaluate what the graph looks like for our exponential functions, you can just try substituting the values of x. So we get here, if x is 0, you will always get a value that is 1. So unlike our logarithmic function that we have 1, 0 ordered pair, in exponential functions what we get is 0, 1 ordered pair. Okay, and then if we try to have more values here, what we get is just an increasing values for our x, and values that are hugely increasing in terms of y. Okay, so it goes something like that. But does this graph will this graph still go down, like downwards? So the thing is, if for example you substitute a value that is negative here in x, let's say x equals negative 2. So what you will get here is f of negative 2 is equal to e raised to negative 4. That is 2 times negative 2. So e raised to negative 4 is actually equal to 1 over e raised to 4. So even though you have values that are negative for x, what you will get is simply the reciprocal of the base, and then the reciprocal of that e raised to that number and then the base. So with that, you won't be able to get any negative values here. So in this case, it can still go a very, very low value for y, but it will never cross the x-axis. So does it make sense when the logarithmic function doesn't cross the y-axis and then the exponential function doesn't cross the x-axis, the negative one? So that makes perfect sense because they're more like an inverse function. Later on, you will have you will realize why is it like that. So that's it for our exponential function, and then the hyperbolic function. So these are the analogs of trigonometric functions. So I will not be able to draw the hyperbolic functions, as these are the functions that are located in your hyperbola. Okay, so I'll just be drawing something like a hyperbola here. So remember, a hyperbola is something like this. So it has these asymptotes, and then it has the graph. So all the hyperbolic functions are taken from this graph. I'll be discussing more about this when we get to have the transcendental function and the derivatives of hyperbolic functions. Okay, but to give you a glimpse about it, the the analogs of the 6 trigonometric functions are the sine h of x. So sometimes it's called the sine hx, the sine x, and then the cos, and then the tangent hx. So usually this is read as the hyperbolic tangent of x. So that's how it should be read. Cosecant hx. It's just, you just have to add some h on that function. So I don't want you to pressure yourself understanding these functions. we will be having a separate discussion all about this and even a graph. Okay, so let's move on with the inverse function. So I can't give you a specific type of inverse function, but I will just be giving you a graph probably. So for example, I have a function that looks like this. Okay, so this function is, for example, let's say I have f of x here. So that is an f of x function. So if I wanted to find the inverse of this function, I just need to draw a graph that is x is equal to y, meaning a linear graph that crosses the origin and like a 45-degree. If you would draw this in a what do you call this, the polar coordinate. So what you need to do in an inverse function is that you will get a graph that is reflected upon x is equal to y. So what we get here is the mirror image of this f of x. So this is the f inverse of x. Okay, so that's how the inverse function works. And if you have, let's say for example, an algebraic function, then you will get an inverse of algebraic function. That's why this is written in black, because this is neither an algebraic nor a transcendental, because there are also transcendental function that can be in that has an inverse function that is also transcendental. So with that, therefore we could say that this is neither an algebraic function nor a transcendental function, but we could also say that these inverse functions are can be algebraic and transcendental. Okay, so somewhere it lies in the middle, so I didn't include it in any classification. Now the periodic functions, so some algebraic functions can exhibit this kind of behavior as well as the transcendental functions, so it is more of both of them. So a periodic function is actually what I've drawn before. So this is a periodic function. So the easiest that I can give you is something like the graph of a cosine. So let's say for example I have f of x equals cosine of x. So a periodic function is something that repeats whenever you've obtained a certain value of p. Okay, and we call this the period of that function. How do we get that certain period? So in trigonometric functions, it is very specific. When you get the same answer, then that's the time it is the period of that function. In cosine functions, the period is actually 2 pi. So this is pi, this is pi. This is pi over 2, and then this is 3 pi over 2. So remember, the cosine function has, if you have 0, then it is equal to 1. Then if we have pi over 2, it becomes 0. And then when we have pi, it becomes negative 1. 3 pi over 2, it gets 0. And then, so with that, let's say we have cosine of x plus 2 pi. For example, I have x is equal to, let's say, pi over 4. So cosine pi over 4 plus 2 pi is actually equal to 48, 9. So we get 9 pi over 4. So cosine 9 pi over 4 is also equal to cosine pi over 4. So that's how it goes for the periodic function. And to give you some value, I think it should be square root of 2 over 2. So with that satisfies our condition that p is the period of a function f in such a way that it will just repeat the value when it has the period p. Okay, now we move on to the increasing or decreasing functions, and this is very easy to spot on, especially when you have a graph. So you need to actually graph these kind of functions so that you can easily understand what kind of functions are these. So increasing and decreasing functions, actually some functions are neither, or non-decreasing or non-increasing. Sometimes they're just decreasing. So the case in which a function is increasing is that when we have f of x sub 2 is greater than f of x sub 1 with x sub 2 greater than x sub 1. So this is very easy to understand when we have a linear graph. So remember, if this is x sub 2 and then this is y sub 2, and then let's say for example this one is x sub 1 and then y sub 1. So let's try to have some kind of point here so that it will make sense. Let's say we have 3 0 and then 4 5 6. So we get 6, and then let's try 1 2 3 4, around 6 4. Though this is not the scale, I'll just assume that those are the values. So what we have here is an increasing function. So how do I know that? So if f of x sub 2 is greater than f of x sub 1, given that x sub 2 is greater than x sub 1. So here x sub 2 is greater than x sub 1 since 6 is greater than 3. And then we need to try taking this if this is also true. So with that, this f of x sub 2 is actually the y value or y sub 2. And then this one is y sub 1. So it should be noted that y sub 2 should be greater than y sub 1. And that is also true since 4 is greater than 0. So this is a decreasing function. So this is an increasing function. Now, I think you already have an idea what is a decreasing function. So a decreasing function is something like this. It just goes from left to right, going down. That's how it goes for decreasing function. So if you wanted to understand what is an increasing function, you simply have to take how the graph goes from left to right. So if, for example, I have a graph that looks like this, so this is an increasing function because from left going to right, it increases, or the direction should somehow increases. And then this one is so this one is a decreasing function because as we go from left to right, as we traverse this domain, so as you can see, y decreases. Okay, and then if we have something like this, so if we traverse the left going to right, our y value increases. So this is an increasing function. Now if we try to take a look at this one, so as we go on from left to right, our y value decreases. So with that this is a decreasing function. So that's how it goes for our increasing or decreasing function. Now, last one is about the bounded functions. So the very first graph is actually a bounded function, the constant one that I have placed some endpoints to that. So I'll also be doing something like this. Okay, so this is a linear graph, but it is not, it doesn't extend to infinity. So if, for example, I have a graph that is, let's say 3x plus 4, though this is not 3x plus 4. So with this graph, this will extend indefinitely if this is just our equation. But if we do something like x should be, let's say 10, x should be less than 10 but greater than, let's say, negative 4. So with this restriction, or equal. So with this restriction, then our graph would just be from, let's say, 1 2 3 4. So something like negative 4 and then 1 2 3 4 5 6 7 8 9 10. So something like that. You shouldn't scale this. I just wanted to show you how it looks like. So with that, the graph should just end here at this point here, from negative 4 to 10. That's how it goes for our bounded functions. So for every f of x, the absolute value should be less than m for all the x or the x values such that it is an element of the interval. So there should exist a real number, m greater than 0. So that's how it is explained when we use graphs, kasi sometimes it's so difficult to understand when it is given as a definition. So what bounded functions mean is that if a function that should extend indefinitely would be bounded by a certain values in the interval of x, then it is a bounded function. Okay? So pag tinigil natin yung supposedly mag-extend na line, then that's a bounded function already na. And I forgot to include here one of the most confusing, probably confusing function, which is the odd and even function. So it's neither an algebraic nor a transcendental function. So let me just write it somewhere here. Okay. So when we talk about odd or even functions, so these odd, I should be using a color that is not transcendental. So when we talk about odd or even functions, so these are functions that, these functions are those functions that would satisfy this condition. This is odd when f of x, when f of negative x is actually negative f of x. And then this is even, or the function is even. So we let f of x our function. Okay, so we let f of x our function. Sorry for the very bad handwriting. So odd and even functions are those in which if we have a function f of x and we set f of negative x, then we'll get a negative f of x. And it will be an even function if we get f of negative x, which is still equal to f of x. Okay, so it doesn't make sense. It doesn't make sense when you explain something like this, no, especially for most cases. So I need to give an example for odd and even functions. So let's try having some easy ones. Okay, so let's try having for f of x equal to negative x cubed. I'm sorry. Let's just make it x squared first, and then okay, the easy one. Okay, so if we substitute negative x from the expression, so what we do here is that we make this x negative. So what we get here is simply x squared. This one is the same as the original equation. So therefore, if this is the same, then we get an even function. So this is an even function. Now let's try doing something like x cubed minus x. So if we have something like this, then we might as well want to substitute negative x from the equation. So we will get here negative x cubed minus negative x. And then what we'll get here is this one is negative, so what we have here is negative x cubed and then plus x. So f of negative x is negative x plus x. And now if we wanted to try to factor out negative, so negative 1, so what we'll get here is negative x cubed minus x. And this f of negative x is equal to the negative of x cubed minus x. Since, remember, f of x is actually equal to x cubed minus x, then we can simply substitute this as f of x, since this is x cubed minus x. And since we have a negative here, that is negative f of x. This satisfies the condition f of x is equal to negative f of x. So this one is an odd function. Okay? So that's how it goes for our even and odd functions. Now let's try having another example. Let's say f of x is equal to, let's say x squared plus x. Okay? So with that, let's try substituting negative x from the expression. So what we get here is a negative x squared minus x. And therefore, we get equal to x squared minus x. Now, if we wanted to do something like factor out negative, what we will get here is negative of negative x squared plus x. So these two expressions here x squared minus x, or negative of negative x squared plus x, doesn't have any condition that satisfies these two, odd or even, since this is not this is not an even function, since though x squared is the same, this positive x is different from negative x. Likewise, if you wanted to check on if it is odd, this positive x is correct, but negative x squared should have been positive, so that you can actually substitute to f of x. So with that, this is neither odd nor even. So it's just neither of the two. So yeah, so not all functions are odd or even. Most of the functions are neither odd nor even. So that's it for our odd or even functions. So technically, we do have 15 kind of general functions. Okay, and we'll be ending our first discussions with a simple test that you can just simply answer on your seats right now. So, which of these are considered functions? So, let x be the independent variable and y the dependent variable. The rest of the letters assume a constant value. So, I'll give you some 10 seconds probably to answer this, or 5 seconds. Okay, so the timer starts now. 5, 4, 3, 2, 1. Actually, I'm just joking. You need to pause this video and do a 1-minute solving for these functions, so that we can actually evaluate it and find if these are really functions. Okay? So I hope you paused the video and you already have the answer. So let's check your answers. So is this the first number a function or not? So if your answer is function, if your answer is function, then you're correct, because y equals e cubed is actually a constant function, and e being a constant value, since it's already said here that the rest of the letters assume constant value, then it should be a constant function. And by the way, when we have e in the expression, we usually refer this to as the Euler's constant, which is around 2.7 value. Anyway, so let's proceed. Number 2. So if your answer is this is a function, then you're correct, because 3x is equal to 4y plus x can be rewritten as 4y is equal to simply 2x. And this is a linear function. Okay, I hope you have no more questions, but if you wanted to review it, then you could just go back to the video. So number 3, let's try x squared y plus 3y equals 2x minus 6. It looks quite complicated, but still the answer is a function. So how did it become a function when it has actually a we call this an implicit expression? Later on, you will be given some of those kind. So yes, it's true that y is multiplied with x squared, but remember, if you can just factor out this x squared plus 3 from y, and then 2x minus 6, what we will get here is simply y is equal to 2x minus 6 and then x squared plus 3. And remember, these are all in x terms, so we can simply say that y is equal to p of x over q of x. And this is very much familiar with rational expressions, because rational functions are given in such a way that they are separated by the fraction line, and then p of x in the numerator with the degree n. So in this case, n is equal to 1, which is the degree of our x, and then we have here q of x with the degree of our numerator being 2. So this is still a function. Okay, so with that, let's move on with number 4. Y squared is equal to x squared minus 3. So the answer is not a function. So this is just a relation. Why is that so? Because if you wanted to draw the graph, you can just simply do something like y squared minus x squared equals negative 3. And then if that's the case, then how do we solve something like this if it is in negative? So we just wanted to do something like x squared minus y squared is equal to positive 3. So now it makes more sense that this is some kind of hyperbola, okay, with the origin at the center. Okay, so that's how it is for our number, for and of course a hyperbola, ellipse, and circle, those are not functions. And then the next one is x equal to bc. So if b and c are constant, then we can just simply do something like, for example, x is equal to 4. This is almost the same as this one. So with that, or it can be x equals 5, so whatever a constant value that it can assume. So with that, the answer is a relation, because even though it is a constant, the graph should look like this. Okay, if this is the Cartesian coordinate plane, then what we will get there is just a vertical line. And a vertical line is actually not a function, because a vertical line, as what we have studied before in your high school, a vertical line actually can give you an answer if the function is, if a relation is a function or not. So we call those tests the vertical line tests. So remember, a vertical line test is a test that is done for graphs of a of a relation, in which a relation should not intersect that that vertical line at least more than once. No, I mean, it should not intersect the vertical line more than once. So that's the perfect definition. So what do I mean by that? So let's just try drawing some test vertical lines here, so that we can simply check on if these are really functions. No, so we could just always do something like drawing vertical lines, and it should not always intersect. I mean, it should intersect just once. Okay, so with that, this is just, and you can draw as many vertical lines as you want, as long as it is infinity. So I just tried drawing some vertical line, and it didn't intersect more than once. Okay, so that's correct. And then this one is also a function because it doesn't intersect the graph twice. This is also a function. This is also a function. So you can just browse over here and just take a quick look. These are all functions. It will not intersect the graph, okay, more than once. Now, so how does it look like when it intersects the graph twice? So it looks something just like this. I sounded like, I don't know. It sounded like lyrics of the song. So this is a circle. So if we try to draw some vertical line here, so that's the vertical line test. And as you can see here, this point here is the first intersection, and then this is the second one. So this is not a function. So this is not a function because the vertical line test actually, intersected this graph twice. Okay. So another one is something like this one. Okay. So if I draw a vertical line here, it will intersect a lot of points here in the graph. Actually, it intersected the graph 1, 2, 3 three times, and then for this one 2 times. So this is not a function. So these are all the things that you will need to somehow review and remember for our discussions, for our preceding discussions, because these are just the introduction of all the things that you have learned in your high school. So I hope you've refreshed your memories regarding all this stuff that we have discussed today. So I'll be continuing our discussion with limits and continuity. So yeah, I hope that you also have some advanced reading for those subjects so that you might you can answer all the simple tests like here that we have here, and probably just just keep chilling, since these topics here for our preliminaries are not that difficult as what you might always think. Okay, so with that, thank you and see you on. See you. I can't see. Just see you. Okay, see you on our next video. Okay, so bye.